Heavenly Father, thank you for your love this day and the ministry of your Holy Spirit operating in and through us. And Father, we don't know what you're doing, but you are active and alive. And you have a concern that the lives that we've been given will really glorify you, will bring honor and praise to your name, not just in some religious sense, but the reality of living in a human bodies. And you know who you're living in, Lord. You're not confused. You didn't call somebody next to you and get the wrong person. You knew who you called, and we wouldn't be here if you not called us. So help us to embrace everything you have to give and make us a blessing on this campus. Ministry can happen right here on this place, just as real as in town or anybody else, any place else. So help us to take opportunity and respond to truth in Jesus' name. Amen. Okay, so I'm going to start out with with that's what you have probably. There we go. So this is our solar system. This was, I passed out that sheet last time. Everybody have that, I assume. So, yeah, that was the last one. I didn't know whether I'd get to it last time. I didn't. So this is our solar system. So this is just, I'm not going to take much time to talk about this. This is just kind of a sweep and a promise. You know what that is. So, a family of objects, our solar system is a family of objects that revolve around the sun. So, they revolve. Now, they rotate themselves. We rotate, once a day, we rotate. But as a body, they revolve around the sun. The earth revolves around the sun. So there are two groups. One is terrestrial planets, that's the inner Mercury, Venus, Earth, and Mars. And they have some characteristics, these terrestrial or inner planets. They're smaller, they're more dense, more rock, smaller amount of gas, thinner atmosphere, less gravity. So the larger the object is, we saw last time when the guy was talking about the Parker Space Probe that is looking at the sun, and it was 5 sun diameters away, and because of that, because of the diameter of the sun, its gravitational pull, and so it's traveling at 400 and some thousand miles an hour as it moves around the sun, because that gravitational pull is so great, the sun. So, but that's what these are. The terrestrial or inner planets have these characteristics. Then you have the asteroid belt, and then you have Jovian planets, which are the outer planets. So you got 4 inner planets, 4 outer planets, Jupiter, Saturn, Uranus, and Neptune. They're larger. They're not smaller, they're larger. They're less dense. So quite a bit less dense, 5 times the density of water. These are only, the average is 1.5 times the density of water. So there's less rock instead of more rock, greater percentage of gas, smaller gas. So they're opposite one thing after another. They have a thicker atmosphere and more surface gravity. So they've got more gravity. So the gravitational pull is larger, which keeps the atmosphere in place. The moon doesn't have any atmosphere because it doesn't have any gravitational hold. So Pluto is included because 7 moons in our solar system are larger than Pluto, and Pluto is hanging around with a bunch of ice balls up there anyway, so they decided that they wouldn't. It's too bad, made a lot of people sad. I mean, it's nice to have Pluto out there, it's just, well, anyway, the dog is named after a famous dog, so that may be part of it. So, I thought this was interesting. That's why it's here. Escape velocity. Escape velocity. It's the speed that an object needs to be traveling to break free from the Earth's gravity and leave it without further propulsion. So it needs to be going so fast to get out of the Earth's gravitational pull. For example, a spacecraft leaving the surface of the Earth needs to be going 7 miles per second, or nearly 25,000 miles an hour, to leave without falling back to the surface or falling into orbit. So it needs to be going that fast to get out of the gravitational pull of the Earth. So that's escape velocity, how fast it needs to be going. The escape velocity is greater on the Jovian planets, those 4 larger outer planets. Gases have a greater difficulty escaping from them or evaporating from them because there's more to hold them in. There's a greater gravitational pull to hold the gases in. Hence, they have a thicker or more dense atmosphere. All of them do, than certainly the inner planets. They're much colder because they're farther away from the source of heat, which is the sun. So their colder environment contributes to their denser atmosphere, as molecules move slower when it's cold. So they're farther away from the heat source, which is the sun, and they have a greater gravitational pull, which holds the atmosphere there. They tend to be more dense. So to enter the Earth's atmosphere, to come in, if you're outside the Earth's atmosphere and you're coming back in, like the Apollo ones that went to the moon, so they went outside the Earth's atmosphere, and then they had to come back in. In the 60s, they had calculated that in order to get into the Earth's atmosphere, they had to be traveling right around a 6-degree angle to the edge of the atmosphere, where a 6-degree angle. If it was less than a 6-degree angle, the surface area of the ship would hit that and it'd go back out into space. If it was more than a 6-degree angle, it would burn up because of the friction it would meet coming in. It just, it's boggling to me. And men were manned in these spacecraft that went outside the atmosphere, and they had to get them back in. And to get a spacecraft that's that far away, coming in at exactly the right angle. And if it was too steep, they'd burn up, and if it was too shallow, they'd go scooting back out into space. I mean, the particular and exactness of that. Now, I think approximately 6 degrees, so there's a little bit of variance, but not a whole lot. So, and that's about the thermosphere, the edge of the thermosphere, rough edge, is about 75 miles up. So that's what they were doing. But a smaller approach, the thin air, even the thin air that's up there is very thin, but it would create enough lift to bounce it back. And if it's too steep, the intense friction caused by the spacecraft's high-speed collision with air molecules would create enough heat to melt the heat shields and itself in a matter of minutes. I think wasn't there a movie where they had to deal with the heat coming in? Was that Nepal? That might have been one of the, I'm not sure what it is, so I'm not recommending it, because I don't remember, but I've seen it. I've seen something that talked about it got very hot in the capsule, because they were struggling to get this thing positioned right to come in to the atmosphere. So anyway, I thought that was an interesting piece. So you've got very little on this particular sheet, but you do have, there's a difference between the Jovian planets and the inner planets, the terrestrial, which are the inner, Jovian outer, and they're just reversed. If you get one down, then the others are just a reverse to that. Smaller, larger, more dense, less dense, more rock, less rock, thinner atmosphere, thicker atmosphere. So more gravity, less gravity. So that should be okay. So that should be that one. And then we're going to step into this Earth-Sun relationship business. At least I'm going to try to step into that. Okay, hopefully. Good. So, Earth-Sun relationships. The Earth intercepts only a very small part, only a minute percentage of the energy given off by the sun. Less than 1/2 billionth. So less than 1/2 billionth of the energy that's given off by the sun. So it's giving off this energy in all directions. So it's not just what's pointed at the Earth. It's given about all directions. But it's given, we get a very small. But this is, however, several 100,000 times the electrical generating capacity in entire United States. So it's just a little bit, but it's energy from the sun is undoubtedly the most important control. Should probably remember that. Energy from the sun is undoubtedly the most important control of our weather and climate. Solar radiation represents more than 99.9% of the energy that heats the Earth, drives the oceans, and creates winds. We're going to talk about how it does those things, particularly how it drives the winds or creates winds. We will talk about that as we proceed. Probably the next section we'll deal with that. So, motions of the Earth.
Could you go back for just a little bit longer?
Yeah.
Most important control, okay.
Can you keep it?
Rotation is the spinning of the Earth on its axis. That's rotation. It's not the same as revolution. Revolution refers to going around the sun. We revolve around the sun, we rotate as the Earth spins about on its axis. So we're in orbit. We are in orbit around the sun, and the Earth is traveling, according to science, at more than 66,000 miles an hour in an elliptical orbit around the sun. So it's not circular, it's elliptical. And the average distance to the sun is 93 million miles. So that's the average. It's about 91 at one end, to the closest, to 94.5 million miles to the farthest away. So the average of 93 million miles. That's just an average. It varies during the course of the year. Here we have this. So obviously from this drawing, probably not to scale. Well, it's not to scale because the Earth is pretty big here. But, so perihelion is when it's closest to the sun, and then aphelion is where it's farthest away, and this is 94, about 94.5 million miles away, and this is about 91.5 million miles away. So we're closer to the sun, farther away to the sun at those particular times, and then we're in an elliptical orbit. But that's the closest it is and the farthest away it is. And about January 3rd is when it's closest, and July 4th when it's farthest away. Variations in the amount of solar radiation received by the Earth as a result of slightly elliptical orbit. So, variations in the amount of solar radiation received by the Earth as a result of its slightly elliptical orbits are nevertheless slight and of little consequence in explaining major single temperature variations. The 3 million mile difference accounts to about 3%. It's not significant. So that difference in how close it is, the closeness of the Earth to the sun, really doesn't make a lot of difference in the overall situation. It's a very small part, and it's not enough to make a tremendous difference. The gradual but significant change in the length of daylight certainly accounts for some of the difference we note between summer and winter. A gradual change in the altitude, the angle above the horizon. So you look out, we see sunsets, we see horizon out there. If you're on a beach, you're looking out the ocean, you see this horizon out there. So it's a difference in altitude above that. And the sun, so the sun will rise, and it'll be twice a year. It's going to be centered right over the equator, and it's going to go up north to 23.5 degrees, and then back, and then south 23.5 degrees. So that's what the sun is doing. Its highest position, where the rays are directly over, is the equator, and then up to 23.5 degrees, and then it'll come back and go on the other direction. So that's where the suns are directly overhead, 90-degree angle. So, seasonal variation in the altitude of the sun affects the amount of energy received in two ways. When the sun is directly overhead, the solar rays are most concentrated. When it's not overhead, when it's coming, the lower the angle, it's less intense. For a number of reasons. It's got more atmosphere, I'll get to that. So, the altitude of the sun affects the amount of energy received on the Earth's surface. You should put a star by this, because this is something that I would speculate you need to know. Two ways. When the sun's directly overhead, it's maximum intensity. The lower the angle it is, like not directly overhead, sorry, I can't, maybe I've got it. Yeah, good, okay. It's got to cut through more atmosphere. The lower the angle it is. Okay, so here we have two illustrations. Rays striking at a low angle, must cover a larger area. The same rays, the same amount of radiant energy coming in December in the northern hemisphere, that's in the northern hemisphere, they cover a much larger area. So overall, they tend to be weaker, where in June, the sun's rays are more directly overhead, so there's a smaller area. So they're more intense here, there's less intense here. That's what that little diagram is saying. Less intense when the sun is at a greater angle, more intense the more directly vertical it becomes.
You go, Will.
So the longer the path, and that this does a couple of things. So when it comes in this angle, it's coming through a lot more atmosphere. The sun is up here, it's coming through atmosphere, certainly. But this, where it's coming at an angle, it's coming through more atmosphere, so there's more possibility for this radiant energy that's coming in wavelengths from the sun to be absorbed and refracted, or reflected, and scattering. So the atmosphere can scatter, absorb, or kick back the incoming radiant energy. So there is even less that are coming and finding a nice space to hit the earth. So all those go into reducing the intensity at the surface. Now what it does at the surface, it does other things, but for right now, that's what we're talking about, how it heats. So the lower the angle, the more spread out and less intense solar radiation is it reaches the surface. And first, where it's directly overhead or close to, it's more concentrated. The Earth is spherical, hence any given day, only places located at a particular latitude receive vertical 90 degrees. I have a globe, but I don't have one. But receive 90-degree rays from the sun. As we move either north or south of this location, the sun's rays strike at ever decreasing angles. What causes the yearly fluctuations in the sun angle and length of daylight? They occur because of the Earth's orientation to the sun. That's what continually changes. The Earth's axis is not perpendicular to the plane of its orbit around the sun, but instead tilted 23.5 degrees. Let me just put this up a little higher. So, because this is angled 23.5 degrees, that's why. Where the vertical rays may be here and they hit, this is the Tropic of Cancer, this is 23.5 degrees up from the equator, and this is 23.5 degrees below the equator. Tropic of Cancer is above, Tropic of Capricorn is below. So you get sunlight hitting, so it's hitting this, if it's hitting here at the Arctic Circle, there's a point where it's more intense. This would be right here, and this would be less intense. In fact, it won't even, this part right here won't be covered. So I'll show that here. This is June 21st. So this is in the summer. This is the summer solstice. So the Arctic Circle is getting sunlight. It gets it all night long. And here, it's dark for the day. And in the winter, at the winter solstice, this would reverse. So this is June 21st. This is what it's looking at. The vertical rays are hitting at this particular time. There is the sun is as far north as it's going to get, 23.5 degrees northern latitude from the equator. This is the latitude marks. So this is equator, and this is 23.5 degrees. So this up here is illuminating the whole Arctic Circle up here, where in the south it's in darkness, and then that will be reversed at the winter solstice. So this is December 21st, the winter solstice. So This is 23.5 degrees below the equator, and that's as far as these vertical rays go. They don't go any lower than that, and they don't go any higher on the other. So the Tropic of Cancer and the Tropic of Capricorn are the maximum in both the northern and southern regions that this direct sun's rays are. This is directly, vertically over this point. So where we live here, we're not gonna get that. We're above that. Now, if you live below the Tropic of Cancer or above the Tropic of Capricorn, you're gonna get days where the sun's rays are directly overhead. If you live on the equator, it's gonna happen twice a year. So one day each year, the axis, such as the northern hemisphere, is leaning 23.5 degrees toward the sun. 6 months later, when the Earth has moved to the opposite side of its orbit, the northern hemisphere leans 23.5 degrees away from the sun. On days between these extremes, the Earth's axis leans amounts of less than 23.5 degrees. At this time, the vertical rays of the sun strike 23.5 degrees north latitude, a line known as the Tropic of Cancer. For people in the northern hemisphere, that's June 21st or 22nd, known as the summer solstice. We have in the northern hemisphere, we have the summer and the winter. The summer solstice is here. The winter solstice is in December, December 21st or 22nd. And that would be the reverse for living in the southern hemisphere. The southern hemisphere, you'd have their winter solstice where we're having our summer one, and they would have their summer where we're having our winter. It would just be reversed. And September 22nd or 23rd and March 21st or 22nd are the dates where the sun is directly over the equator. The vertical rays of the sun strike the equator. So, the autumnal equinox for the northern hemisphere, that's the autumn equinox, is when it's hitting the equator, and then on March 21st or 22nd is the date of the vernal or spring equinox, when it's also, the sun is directly over the equator. So there, as this shows, there are two times. This is the summer, so this would be where the rays are directly, here's, the rays would be right directly over the equator here, and then they'd be directly over the equator here, and this would be the spring equinox and the autumn equinox, as far as we're concerned in the northern hemisphere.
Mr. Nelson.
Yo,
So do you guys get sun at night during the summertime?
no, we don't. You do. So you've got to be above, I think it's 66.5 degrees. If you're above 66.5 degrees latitude, you'll get sun at that portion. But no, we don't. It gets dark down here. So, the length of daylight versus darkness is also determined by the position of the Earth in its orbit. So let me see if this will do the first 7 minutes.
And Doug. You'll be back! Emus can't help people.
I can say pirates.
Hello, ETS 113 students. This is Dr. Shragi here to help you today learn how to compute sun angles based on Earth-Sun geometry. This is important because the sun angle has a lot to do with the amount of heat that we receive from the sun at any given location. It's probably your own experience that on different days of the year, the sun is different heights above the horizon. For example, in this picture, clearly this person experiences a sun angle that is greater in June than in December. And of course, we know that the weather is very different in June and December in terms of how much heat we're receiving from the sun. This is important because of the concept of beam spreading. Even though each beam from the sun contains the same amount of heat, when the sun angle changes, that amount of heat is spread over a larger area or a smaller area. For example, in the tropical picture off to the left, you can see that 1 unit wide beam of sunlight hits the ground and covers an area 1 unit wide. The sun is directly overhead, so there's no beam spreading. On the other hand, if you go with the picture all the way to the right, with the igloo, you can see that a width of a beam of sunlight of the same width as was in the first picture, because it's now coming in at a very low sun angle, spreads out over a large region, 2 units wide. The same amount of heat from the sun has to heat up a larger area, and so the amount of heating is less. The rays that we receive from the sun are effectively parallel. The sun, of course, sends out heat in all directions, but we're so far away from the sun that only the beams that are coming in basically exactly our direction hit the Earth. So they're basically parallel by the time they hit the Earth's surface. But that doesn't mean that everyone experiences the sun in the same direction. Here I've drawn 4 little people on the plot. If you consider the point of view of each of these people, you can see that the sun angle changes quite a bit at different latitudes on the Earth's surface. The yellow man, who's in the tropics, is experiencing the sun directly above him. He has a very high sun angle, whereas the pink man near the pole has a very low sun angle. The sun's rays are all coming from the same direction, but because of the curvature of the Earth, they're all experiencing slightly different sun angles, and therefore different amounts of beam spreading. As discussed in class, the Earth revolves, of course, around the sun in an elliptical orbit, although the fact that the orbit is elliptical is not what's important for the seasons and for sun angles. What is important is the fact that the Earth is tilted on its axis. Here I've highlighted the axis of the Earth, and you can see that in all cases the Earth's axis is pointing off in the same direction. As it happens at the present time in Earth's history, it's all pointing in the direction of the North Star, Polaris. Although that's just a coincidence, it just happens to be a bright star in the general direction the Earth's axis is pointing. Why does the Earth always point in the same direction? Because nothing is pushing the Earth to point in different directions. If we zoom in on the situation in June, when the Earth's axis is positioned in this way, you'll see that the northern hemisphere is tipped towards the sun. Now that doesn't mean that the northern hemisphere is closer to the sun than the southern hemisphere is. That's not what I'm trying to say here. What I'm saying is that locations in the northern hemisphere are experiencing higher sun angles than locations in the southern hemisphere. I'm actually highlighting here a very specific date. This is the June solstice. It happens about June 21st or June 22nd on any given year. And on this location, this is as much tipped towards the sun as the northern hemisphere is going to get. This is going to be the longest day of the year in the northern hemisphere. Longest in terms of length of daylight. The sun is going to be directly overhead at 23.5 degrees north, the Tropic of Cancer. That makes the Tropic of Cancer Earth's solar declination on June 21st. Remember, the solar declination is just the latitude at which the sun is directly overhead. Look at the North Pole. As the Earth rotates on June 21st, the North Pole is never going to be on the dark side of the Earth. At this time of year, the North Pole is experiencing 24 hours of daylight. Look at the South Pole. As the Earth rotates about the axis, the South Pole will never rotate into the part of the Earth that is illuminated. The South Pole then is experiencing 24 hours of darkness. Let's consider the situation then in the opposite, 6 months later in December. In December, the northern hemisphere is now tipped away from the sun. southern hemisphere is tipped towards the sun. And in fact, I've highlighted a very special day here. This is the December solstice. It happens by December 21st or December 22nd. And on this day, the solar declination, the latitude at which the sun is directly overhead at noon, is 23.5 degrees south. 23.5 degrees south is the Tropic of Capricorn. So that on December 21st, the solar declination is as far south as it's going to get. This is the longest day of the year in terms of length of daylight for the southern hemisphere. In fact, you can see at the South Pole that the South Pole will never rotate out of the illuminated side of the Earth. So there are 24 hours a day of sunlight in the South Pole, whereas this time of year, the North Pole is experiencing no daylight at all. In fact, all locations north of the Arctic Circle are experiencing no daylight at all on December 21st. So this will be the shortest day of the year in the Northern Hemisphere. Just to show an example of a equinox, let's look at September. September 21st and 22nd, I'm sorry, I guess this is actually March. March 21st and 22nd are examples of an equinox. On an equinox, all locations on Earth are experiencing a 12-hour day and a 12-hour night, hence the term equinox. March 21st and 22nd then are the March equinox. There's also a September equinox on September 22nd and 23rd. All locations on Earth are experiencing a 12-hour day on the equinoxes. The sun is directly overhead at the equator on the equinoxes. In other words, we would say that the equator is the solar declination on these.
So the equinox, you have the solstice, where it's vertical here, 23.5 degrees, or here, the equinox is where it's right over the equator, the equinox. So, comparison. New York City, which has 15 hours of daylight on the 21st of June, and 9 hours on December 21st. Those are the solstice, where it's in June 21st, it's the farthest in the northern latitude the sun will get, directly overhead, and then in December, it'll be the farthest it gets to the south, and those are the solstices, and so it makes it a lot different. There are people out there on the street, and here are people out in the street, but there's not as many, and having a harder time walking. But it's not all bad. See, those guys are smiling. Just saying. So the farther north of the equator, the longer the period of daylight during the summer solstice, until the Arctic Circle is reached, where the length of daylight is 24 hours. Although the altitude of the sun is the main control of temperature. That would be a good question. What's the main control of temperature? Attitude, altitude. It's not the only control. Seasonal fluctuations in the amount of solar energy reaching places on the Earth's surface are also influenced by variation in sun angle and length of daylight. So the main control of temperature is the altitude of the sun. But additionally, there can be variations in the angle of sun and in the length of daylight. And that's it, huh? Okay. So I,
Can you go down a little bit? Like way down,
like,
like to the last.
There's a down.
Keep going. I want the last one.
that's there?
That's it.
Okay. So, So these are looking at our atmosphere. So we are this is the structure of the atmosphere. So the thermosphere, when I mentioned about spacecrafts coming in, the thermosphere, they're saying the thermosphere is the top one. I don't know if I have a. Well, we might do this in a minute, but I think this would be okay to do. So right here, you don't have this, but this is looking at the altitude in miles from sea level. And this is the different kind of electromagnetic radiation that is coming in to the Earth. So we get radio waves, microwaves, infrared, visible light is a little piece here, ultraviolet, X-rays, and gamma rays. And fortunately, our atmosphere, that's distracting. It's like eating potato chips in class. Don't do it. Thank you. So the gamma rays and X-rays and ultraviolet rays are taken out to a large degree by our atmosphere. I mean, some get in, but our atmosphere is designed to take out these guys. Visible light comes all the way in. Some of the infrared and microwaves are taken out as well. And then the radio waves and the radio waves particularly are able to come through our atmosphere without interference. They're very long. These are, as we've said before, these are very long, very, very long waves. So some of them apparently aren't, but that's just generally. So different types of electromagnetic radiation penetrate to different altitudes before being blocked by the Earth's atmosphere. Only visible light and certain types of radio waves can penetrate all the way to sea level. So, but some of these UV rays, it's not that they are completely blocked. Some get through, hence we need protection from some of these rays, which is what they want to sell you. So at this structure, you need to be aware of what this is. You need to be aware of what's on your, as you look at this on the far left, the troposphere is about 7.4 miles up. Then you have the stratosphere, goes from there to about 29 miles. Then you have the mesosphere that goes up to about 52 miles, and the thermosphere goes up the rest of the way. This is important to note. As you go up, you'll see, starting at land surface, you go up and temperature falls in the troposphere, the area that's closest down to where we live, up to our atmosphere. What's going on, our clouds and the rest of that, is usually operating right around within the 7-mile range, and the temperature falls as you go up. The higher you get, the lower the temperature gets. And then you get, when you start to get in the stratosphere, where planes fly, the temperature remains constant, but then it increases. So the temperature gets warmer. If you put your hand out the window, if you wouldn't be sucked out the window, if you were in a plane and you could put your hand down the window, it wouldn't feel so warm because there's so few molecules out there and they get fewer and fewer as you go up. That's why that guy said, as you are approaching the sun, where the photosphere, the surface of the sun is like 6,000 degrees. But when you get out to the corona, you're talking about millions of degrees. But there's so little density of material out there, you could probably, if that was all you were dealing with, you wouldn't know it. But the radiant heat coming from the 6,000 degree sun is gonna make you a crispy critter if you're there. But because the molecules are so far apart, you wouldn't feel the heat, even though they can measure the heat increasing and the temperature is really high, there's not a lot of them. So the temperature, it starts out falling, and then it's consistent, begins to rise, and it gets up to the top of the stratosphere, and it begins to fall. And it falls until you get up to the ionosphere, and then it begins to rise again. So it's the falling and rising of temperatures that demark the different levels of our atmosphere. It's temperature rising and falling, and that's why, because this is a gaseous thing, there's not a line up there that you cross and okay, you're in there. You were there, here, and now you're in there. There's not a line there, but if you could measure the temperature, where the temperature is falling to a certain point and then it begins to level off, well, that demarks the difference between the troposphere and the stratosphere. So that's just something to know, and that's all I want you to know for today, unless the Lord gives you something else.